Dear students, this is Vijay Anand, working as Associate Professor in R.M.K. Engineering College in the Department of Electronic and Instrumentation Engineering. I have taken digital signal processing subject many times. Today we are going to see Unit 5. If you see the syllabus, Introduction, Architecture, Features, Addressing Formats, Functional Modes, Introduction to the Commercial Processor. Let us see one by one. First, Introduction. DSP processor or microprocessor designed for the efficient and mathematical manipulation of digital signals. There are two types of DSP processor. One is general purpose DSP processor and second one is special purpose DSP processor. General purpose digital signal processors are basically high speed microprocessor with architecture and instruction set optimized for DSP operation. Special purpose digital signal processor consists of hardware designed for specific DSP algorithm such as FFT, PCM and filtering process. These are the different Texas Instrument DSP processor family that are available in the market. If you see C2000 series, it is used for motor control, storage and digital control system. C5000 series used for wireless phones, internet audio players, digital still cameras, modems, telephone and VoIP process. C6000 series used for multi-channel and multi-functions applications, communication infrastructures, wireless base stations, DSL, imaging and multimedia service and video applications. DSP applications like MPEG audio, portable audio, digital cameras, cellular phones, wearable medical applications, storage products, industrial control, networking and military applications. How to select a digital signal processor? First point is architecture features, size of on-chip memory, special instructions and input-output capabilities. Execution speed, clock speed, number of operations performed on one cycle, that is measured as MIPS, million instruction per second. Type of arithmetic, fixed point, low cost and high volume application, whereas floating point it is expensive, that is used for higher applications. Word length, number of bit size like 16, 24, 32, etc. Longer word length, lesser error. Types of architecture. Von Neumann architecture. In 1946, John von Neumann developed a first computer architecture that allowed the computer to be programmed by codes residing in memory. Von Neumann architecture, the CPU can be either reading an instruction or writing data from or to memory. Both cannot occur at the same time, since the instruction and data use the same signal pathways and memory. The von Neumann architecture consists of three buses: data bus, address bus and control bus. Data bus are used for transport the data between CPU and its peripherals. It is bidirectional. The CPU can read or write data in the peripherals. The address bus uses the address bus to indicate which peripherals it wants to access and within peripherals with specific registers. The bus carries signals that are used to manage and synchronize the exchange between the CPU and its peripherals, as well as the indicates if the CPU wants to read or write the peripherals. Harvard architecture. Harvard architecture physically separates memories for their instruction and the data, requiring a dedicated bus for each of them. Instruction and operands can therefore be fetched simultaneously. Most DSP processors use a modified Harvard architecture with 2 or 3 memory buses, allowing access to the filter coefficient and input signals in the same cycle. Since it possesses 2 independent bus systems, the Harvard architecture is capable of simultaneous reading an instruction code and reading or writing a memory or peripherals as part of the execution of the previous instruction. Modified Harvard architecture use DSP multi-port memories that has separate bus system for program memory and data memory and input-output peripherals. The third one is VLAW architecture, very long instruction word architecture. It is essentially a concatenation of several short instructions and require multiple execution units running in parallel to carry out the instruction in a single cycle. The very long instruction word processor consists of architecture that reads a relatively large group of instructions and executes them at the same time. The VLAW processor combines many simple instructions into a single long instruction word that uses different registers. The advantages are increased performance, better compiler targets, potentially easily to program, potentially scalable, can add more execution units for fast processing. The disadvantages are a new kind of programmer or compiler complexity. Program must keep track of instruction scheduling, increased memory use, high power consumption and misleading million instruction per second ratings. MAC, a multiply accumulate unit. It can multiply a 16 into a 16 data. Pipeline. The most of the early microprocessor executes instruction entirely sequentially. After the execution of first instruction, the next one starts. The problem with this is that it is extremely inefficient since the second instruction has to wait until all the steps of first instructions are completed. To improve the efficiency, advanced microprocessor and digital signal processor use an approach called pipelining, in which a different phase of operation and executions of instructions are carried out in parallel. It has fetch, the next instruction is fetched from the address stored in the program counter. Decode, instructions in the register is decoded and increment the program counter. Memory read, reads the data from the data bus and also writes the data to the data bus. Executes the instruction currently in the instruction register and also completes the write process. This is a pipeline example for 4 stages. You can see instruction 1, in first cycle the data is fetched. If you see the second cycle, the first instruction is decoded. Simultaneously, the second instruction is fetched and kept ready. Architecture of TMS320Cx series. It is one of the important questions in this unit, and it is a repeated question. It is a fixed point, a 16-bit processor running at 40 MHz. Single instruction execution time is 50 nanoseconds. Architecture uses hardware plus on-chip peripherals and on-chip memory. It is divided into 4 blocks. First one is bus structure, second one is CPU, third one is on-chip memory, and fourth one is on-chip peripherals. This is the architecture diagram where you can see a data bus, bus structure, maximization of processing power with high degree of parallelism and MAC operations. It has a 4 important bus. Program bus carries the instruction code and immediate operand from program memory to CPU. Program address bus provides the address to the program memory space for both read and write. Data read bus interconnects various elements of CPU to data memory. Data read address bus provides the address to access the data memory space. Central processing unit. It consists of central arithmetic logic unit called as CALU, parallel logic unit called as PLU, auxiliary register arithmetic units called as ARAU, memory mapped register called as MMR, program controller called as PC. Let us see one by one. Central arithmetic logic unit CALU performs 2's complement arithmetic. It consists of 16 cross 16 parallel multiplier, 32-bit accumulator, 32-bit accumulator B register for storing the quotients and reminders, product registers, shifters. 16 cross 16 bit hardware multiplier is capable of computing signed or unsigned 32 bit product in a single cycle. The result is stored in accumulator. Parallel logic unit. It is the second logic in CPU. It executes logic operations on data without affecting the content of the accumulator. It can directly set, clear, test on any data memory locations. The result is stored in first operand memory locations. Block repeat registers. It has four important registers: RPTC, BRCR, PASR and PAER. All are 16-bit length. RPTC, it holds the repeat count in repeat single operation and it's loaded by the RPT and RPTC instructions. BRCR, it holds the count value for the block repeat features. This value is loaded before the block repeat operation is initiated. PASR, the block repeat program address starts register indicates the 16-bit address where the repeated block of code starts. PAER, the block repeat program address end registers indicates the 16-bit address where the repeated block of code ends. Instruction registers hold the opcode of the instruction being executed. Interrupt registers, it is a 16-bit length. Interrupt mark registers individually marks the specific interrupt at required time. Interrupt flag register indicates the current status of the interrupt. Program controller, it consists of following elements: program counter, it has a 16-bit length. Hardware stack, program memory address generation, status and control registers, instruction registers. Circular buffer registers, it has 4 registers. Circular buffer register, it has 5 registers. As 2 circular buffer registers as 2 concurrent circular buffer: CPSR1, CPSR2, CBER1, CBER2, CBCR. On-chip memories of 224 kilo word length of 16-bit length, 64 kilo word of program memory space, 64 kilo word of local data memory space, 64 kilo word of input output port and 32 kilo word of global data memory space. It has a program read only memory, data program single access memory, that is SARAM, data program dual access, that is called as DARAM. On chip peripherals: clock generator, hardware timer, software programmable wait state generator, general purpose input output pins, parallel input output port, serial port interface, buffered serial port, TDM serial port, host port interface, user unmaskable interrupt. Addressing modes. There are 6 types of addressing modes: immediate addressing, indirect addressing, register addressing, memory map register addressing, direct addressing and circular addressing. Let us see one by one. Immediate addressing handle the constant data to the accumulator immediately. For example, LD80, A loads an immediate value of 80 into an accumulator. Indirect addressing, it uses auxiliary register to hold the address of operand in memory. The selection of AR0 to AR7 with the help of auxiliary register pointer is powerful indirect addressing. It has 7 types: auto increment, auto decrement, post indexing by adding the content of AR0, post indexing by subtracting the content of AR0, single indirect addressing with no increment, single indirect addressing with no decrement, bit reverse addressing. Register addressing, it uses operand in CPU registered directly. Address comes from two special purpose memory mapped register in CPU: block move registers and dynamic bit manipulation registers. Memory mapped register addressing, it uses on-chip peripheral registers, first 9-bit representing address of the page, remaining 7-bit representing opcode and operands. Direct addressing, CPU uses the data specified by data page pointer. Data page pointer is a 9-bit field contained in the status register. In this mode, the address of the operand is obtained by concatenating the 7-bit DMA with 9-bit of the data page. Circular addressing, circular buffer starting address register 1, circular buffer end register 1, circular buffer control register.